It's a joint work with my colleague Abishai and I. Okay, so we are going to speak here about two very fundamental problems called the maximum problem and the multiple Mllionaires problem. In both problems, the inputs are private integers x1 to xn, and let's assume for the sake of the discussion that they are secret shared among k parties, even though it is not a limiting assumption for our case. This is just for, we have some ground to stand on. And in the first problem with max p, the desired output is the maximum for those inputs, while in the multiple Mllionaires problem, the desired output is the indices of all inputs that equal the maximum. Now, those are fundamental problems which are natural extensions to the very first problem of multi-party computation that was introduced by Yao in 1982. And each of those problems is reducible to the other, so in some protocols I will solve the MMP, in some I will solve the max P, because once you solve the one, you can then go to the other. And we should focus on protocols that have information theoretic security. So such problems have many applications. For instance, in privacy preserving machine learning, it's relevant for k-means clustering or nearest neighbor, where here we want the minimum, but the maximum, but of course, maximum, minimum, almost same, and or soft maximum neural networks. And in other privacy preserving applications, it's relevant for auctions, voting, or fingerprinting matching. Okay, so we should describe here four approaches to solve those problems. Three based protocols, a monotone representation protocol, I will explain it once we get there, digit decomposition based protocols, and binary search. So the first approach is to use a tree-based protocol. So here we have the, let's say, 8 inputs, and the idea is, by the way, this idea I presented here for binary tree. It was already done in two previous works. The idea here is to simply compute the maximum between every two pairs until we get to the root of the tree, which is the maximum of all the inputs. And here we need to somehow securely compute the maximum of two nodes, of two values. So we base our computation on this very trivial identity that max of A and B are A plus equals A plus the bit which equals 1 if and only if A is less than B times B minus A. So if A and B are protected in some manner, let's say by homomorphic encryption or by secret sharing as I assume here, I will not dig into the details how to compute this securely. Actually, this talk will be almost cryptography free because we want to focus on the high level, on the logic of the protocols, and we should not open up the black boxes of how to perform the secure computations like here, comparison and computations, and you can look it up in the paper. Now, this approach can be also taken when the tree has higher degrees, let's say m degree 3. So here, if m equals 3, we can do this computation until we get to the root, and then we get the maximum. So here, we have to somehow, the building block will be to compute maximum of, in that case, three secret values, A, B, and C, and because m equals 3 here. And how should we do it? So there are several possible approaches. Or we can use an all-to-all comparison algorithm that compares all pairs in that set of m values, and that if we do that, we should get run complexity of 1, which is minimal, but the size will be maximum, will be O of m squared. On the other hand, we can apply here the binary tree approach, which offers a minimal size of O of m, and a round complexity of log m. So this is up to you how to open up this little box of computing the maximum among m inputs. So this is how the round complexity of the tree-based protocols depend on m. If we take m, which is a constant, we should get number of rounds, which is O of log n. If we take m to be some root of n, the number of inputs, we should get a constant number of rounds. Of course, there is a trade-off which is very, very clear here. Okay, next we shall move to another protocol, which I call a monotone representation-based protocol. Here we have only one single protocol. It is designed for inputs that are drawn from a small domain, a very limited domain, and actually we should use it only as a subroutine in our next protocols, so which are digit-based protocols. So let's assume that each input is taken from some small domain, 0 up to q minus 1, and we should represent it by a monotonical representation, namely by a sequence of q minus 1 bits. And instead of focusing on the equation, let's just take an example. If q equals 5, we have 5 possible inputs, 0, 1, 2, 3, 4, and this is how we present 0, this is how we present 1, 2, 3, 4. Of course, the number of ones equals the value of the input. Now, if we do it this way, then, in order to compute the maximum, we simply have to go over each of the columns and then take the OR of the private bits in that column. Now, the beautiful thing is that to compute an OR of n bits, that can be done in a constant number of rounds, independent of n. And that is why that protocol has a constant round complexity, both in the pre-processing stage and in the online stage. It does not depend on n. So let's take an example. Suppose that we have q equals 8, and there are n equals 3 inputs. So this is 5 is encoded this way, 3 is encoded that way, 6 is encoded that way. And then if we go column by column and take the O of the bits in each column, we should get here the monotonic representation of the maximum, which is of course 6. Very, very simple. As I said, the main purpose of that protocol is to serve in what comes next. So what comes next is 2 protocols which are based on digit decomposition. We should start with a binary decomposition protocol. And that protocol, as opposed to the 2 that we had before, will solve directly the multiple Mllionaire problem, not the max problem. Namely, it will not, if the tree-based things and protocols or the monotonic representation first computed the maximum, and from there the identities of the richest or the largest inputs, here we go directly for the MMP problem. And it uses the bit representation of each of the inputs. So suppose that capital B is an upper bound on log 2 of all the inputs of the maximum. And of course, each input can be represented binary by B bits. And that protocol scans the input bits, the inputs bits, from left, MSB, to right as follows. It does this computation from B-1 position to 0 position. It computes some control bit that we call it SB, using that formula. And that control bit decides how we shall update the bits in the next column, namely when you go to the left, either by this update procedure or by this update procedure. And we claim that if we do this computation properly, and then what we should be left with in the rightmost column are exactly one in all the lines, in all the rows in which we had an input that equals the maximum m. The proof of that lemma appears in the paper. So let's do a very, very swift demonstration, even though I don't expect you to follow the details, but just to have an idea of what's going on. So suppose we have 4 inputs, 11, 7, 10, 11. They can all be represented by 4 binary bits, and here you can see the binary representation. I marked by yellow the 2 inputs which I'm looking for, the maximum inputs, this one and this one. What we do is we start with the leftmost column, we compute SB, which is the OR of, the formula was a bit different, never mind now, it's 1, and since it is 1, the value of the bits here are updated by the formula that we had in the last slide. The details are not important right now. Then, in the next column, we get SB equals 0, we get here that kind of update, and so forth, and so forth, and at the end, you have to believe me, what we get is the 1 position, 1 in that row and that row. Of course, all the computations of the SB bits, all the computations of the OR and the if, then, else, everything must be done in a secure manner, and we explain in the paper how to do it securely without leaking any information. These are, as I said, information theoretic secure protocols. Now, so these are the maximum, the 2 maximal inputs as we wanted them to be found. Next, we should discuss an extension to using larger bases. Let's say Q equals 2 to the power of d. It's more convenient to use a base which is a power of 2. So here, it scans the Q digits of the inputs from left to right, and it issues at the end the indices of the maximal inputs. So in spirit, it is similar to what we had in the binary case, but the details are a bit more complicated. Not truly, but there's more substance to the details here, and I encourage you to look in the paper to see how it works. But in spirit, it is the same thing. And here, we need to compute in each column of digits what is the maximal digit that appear there. And for that purpose, we use the constant depth max speed protocol that we showed 4 or 5 minutes ago. So that one is used here in order to compute the maximal digit in each column, and then to decide how to update digits in the next columns in a manner which resembles what we had in the binary case. And I should say that the size of the protocol grows like 2 to the power of d over d, where d is the number of bits in each digit, while the depth number of rounds decreases like 1 over d. Of course, there is a threshold between number of rounds and between the size and number of rounds. That's it. Next, the last protocol is based on the work of Agarwal, Mishra, and Pinkas from 2010. They devised an MPC protocol for securely computing the k-ranked element in a distributed database. Now, we saw that we can use that protocol in order to solve also the maximum problem. And so basically, it boils down to a very simple thing. Given an a priori upper bound b on n, we have to assume something that, as we assumed in the previous protocol, that we have some upper bound on the number on the values of the inputs. Here too, we assume some kind of upper bound. Then the protocol boils down to a binary search over that interval, where's the trick? Where the decision between continuing the search in the lower half or the upper half must be done in a secure manner without revealing information on the inputs to none of the parties. So that's about it. Now let's summarize the results. We conducted very, very detailed analysis, theoretical analysis of those protocols regarding the round complexity and size, both in the pre-processing stage where you still don't need to rely on the inputs, and also in the online phase after the inputs were revealed. And we also conducted experiments where the cryptographic computations were done by secret sharing, as I mentioned in the first slide. And what we get here is this trend. The 3 protocols are the ones that have the highest number of rounds, but the lowest size, where here you have the binary tree. Here you have a 3, 4, 5 degree tree. Of course, the more we increase n, we go back here. Those protocols depend on the upper bound on the value of the inputs or on the maximum. So we have here the binary decomposition, the queue-based decomposition, and the interactive binary search protocol. And this is roughly the trend between those 3 options. And those protocols have a constant round complexity, either if we use a tree of degree, which is O of square root or any other root of n, or if we use the monotonic representation. But of course, the price that we have to pay is in the size of the computation. And I believe that that's it. Thank you very much.
Well, thank you, Tamir. Do we have any questions for Tamir? Do we have any questions online? Oh yeah, question here.
So on the previous slide you showed, you said computation, but it read communication. So for the horizontal axis, you said computation.
Yes.
But it says communication, size.
No, it is communication size. How many bits are exchanged?
So it's not. But, and what is the computational complexity? How do they compare there?
Okay. In
so
time,
every round is the same complexity.
We count the time complexity in terms of rounds.
Okay.
This is the most influential parameter. And in size, we mean how many messages or how many bits you have to exchange between the parties in doing that computation. So it's space versus, this is time in that sense.
Yeah, well, okay.
Thanks, Tamir, again.